Yeah, good morning. Welcome to the first class on Introduction to Quantum Mechanics and Quantum Computations. So I've told you in the introductory class that in order to understand why we need quantum mechanics, in order to understand the special features of quantum mechanics, it is essential for us to initially revisit what we call classical mechanics and understand the basic ideas in quantum mechanics are quite different from classical mechanics. So this comparison can come only when you do some simple things in classical mechanics, and that gives you an idea of how quantum mechanics is different than classical mechanics. So what I'm going to do today is take a very simple example in classical mechanics, which is called the harmonic oscillator. I will do the simple derivation or the features of harmonic oscillator in classical mechanics. I will switch to a video where I would be writing on a paper, and if there is any question, feel free to stop me and ask me. And kindly mute your mics unless you have any questions so that the class will be undisturbed. Thank you. So let us switch to the writing part. All of you are able to see the paper, right?
Yes, sir.
Yes, sir.
Okay. So what we are going to do here is we're going to talk about the harmonic oscillator. So basically, consider a very simple system where you have a spring like this, and then there is a mass attached to the spring. There's another spring here, it's also attached to ball like this. Now this is the equilibrium position, 0. This is the positive x-axis. This is the negative x-axis. What will happen is, if you push the mass to the left-hand side, it will compress the spring, but it will expand the other spring. On the other hand, if you push to the other side, this will expand and spring will be compressed on the other side.
So, for microfocus, there are a lot of government projects in Australia.
Okay, so this is how it will move. Now, what we need to do is the prescription to solve any problem in classical mechanics is to consider Newton's second law, which is F is equal to ma. It's the vector equation. But since we are considering only one axis, which is x-axis alone, there is no need to write it in the vector form. I can simply write f of x, x. So this is in one direction only. Therefore, I write only the component and I don't write the vector equation. So henceforth, I will be simply using f is equal to ma, where fx means f, ax means a. Okay. Now we know that when the spring is compressed, there is a force acting opposite the direction of compression. So you are moving in this direction, and the direction that you are moving in is x or minus x, depending upon which way you are going. But the force will be acting opposite. Therefore, it is proportional but opposite in direction. We know that this can be written as minus kx. Now we got two equations, one here, two here. So we are going to equate these two to get ma equal to minus kx. Or you can also say the sum of all the forces is equal to 0, which is one and the same. This is the standard method of solving any problem in classical mechanics. You basically write down the Newton's second law, and you write down the nature of the force, and sum of all forces should be 0 in this system. Now you write MA as m into acceleration, that is d square x by t square. I'll bring it to this side, it will be kx equal to 0. Now we write usually this d square x by dt square as simple mx double dot plus kx equal to 0. Now I divide this by m, I get x double dot plus k by m x equal to 0. Or this would be x double dot equal to minus k by m into x equal to 0. If you look at this, you see this is x double dot, which is d square by dt square of x. I'll write it in a bracket like this, equal to minus k by m x. What you see here is there is x on the left hand side and there is x on the right hand side. So what this basically means is if you differentiate this x twice, you get back the x again, but there is a term multiplied to that. So now we call this equation or this equation as the equation of motion. Equation of motion. Okay. Now this is another way of writing the equation of motion. Now the equation of motion is telling us that if I differentiate x twice with respect to t, I'll get back the x with the term multiplied here. Now this kind of an equation is called an eigenvalue equation. Because this differentiation is differentiating this with respect to t twice, and I'm getting back x again, but with a constant multiplied. So now let us try to solve this equation. What would be the value of x for which I will get this kind of a solution? What would be the function? What would be this function? So one of the functions that is satisfying this would be a trigonometric function, which is, let's say, cos. But suppose there is cos theta. If you differentiate cos theta once, you get minus sin theta. You differentiate it again, you get minus cos theta again. If you start with cos theta, you get minus sin theta. You get minus here. So you have got that. This plus here. This is cos theta. Differentiate with minus sin theta. But you need k by m here. So if you want k by m here, that quantity should have been inside this. So it's not just sin theta, something into cos theta. Something into cos theta. When you differentiate twice, it will come out twice. Therefore, whatever has come out twice should have been in the form of a root of that value here. If there was root k by m there, it will come out once, it will become root k by m minus. Again, it will come out. It will become k by m. So therefore, quantity inside this should be root k by m. So therefore, we already anticipate that and call this by some number, which is a square of some quantity. Let's call it omega square x. Now, d square x by dt square, omega square x. So now I can easily say that this is going to be cos omega t. But we also need an amplitude. So we put a here. So I differentiate once, I get minus A sine omega t. I differentiate again. I get minus, sorry, omega is coming out here. So minus A, omega again comes out, omega square cos omega. Okay, now you can see that minus omega square is what you have got, and cos omega t, A cos omega t, is nothing but x itself. If you look at this equation, now that is the same as this equation. Therefore, we say that x equal to A cos omega t is a solution. Let's call it 1. Is a solution. Solution of this equation. If I plot this, I will get something like this. Right? So this is x, this is t. This is a solution of this particular differential equation, equation of motion, which means that in time, this mass will oscillate sinusoidally between these 2 points. Now let us look at another feature of this. Suppose I take another solution. Let me take another solution. X equal to, okay, that was x1, let's call it x1, A cos omega t. Let's take another solution, x2 to A sine, or it can be even B sine omega t. Let's see whether this is also a solution. So let me check d square x by dt square, whether it satisfied this equation. If it satisfies this equation, then it's a solution. So let's try this. X is B sine omega t. First derivative is omega comes out, omega B cos omega t. Second derivative is minus omega square B sine omega t. Again, we started with sine omega, B sine omega t, B sine omega t, omega square is multiplied. So this is also a solution. And we know that this is a solution. This is also a solution. Now what I claim is that these 2 solutions, suppose I add them, okay, and I write like this, x1 plus x2, I add it as, write it as x equal to A cos omega t plus B sine omega t. Let's say this is an expression which I've got by adding x1 and x2. Now I claim that this x is also a solution of this equation. Let's call it capital 1. This is the equation of motion. Now I claim that this particular equation, which I call it 3, is also a solution of this particular equation. Let us see whether that is true. Okay, how to do that? So if this is a solution, then I can write x dot double dot equal to minus omega square x1, right? Because it's a solution of that equation, this is true. Similarly, x2 double dot is equal to minus omega square x2. If x is a solution of this equation, I need to show that x double dot, x double dot is equal to minus omega square x. This is what I have shown. Where x is x1 plus x. So let me look at the left-hand side and the right-hand side of this equation. The left-hand side of this equation, x double dot is nothing but x1 plus x2 whole double dot, right? Or d square by dt square of x1 plus x2. That's the left hand side. So how do I do this? I have to differentiate x1 twice. I also have to differentiate x2 twice. So this is nothing but, to get this quantity, I should first get dx by dt. What is dx by dt? X is here, x1 is here. x1 is a cos omega t. So dx1 by dt is a omega minus a omega cos omega t. Similarly, dx1 by dt square is equal to minus a omega square sine, this is sine, this is cos, this is a omega square cos omega. Similarly, I'll do d by dt of x2. What would that be? x2 is a b sine omega t. So d by dt of x2 would be d omega sine omega t. d square x2 by dt square would be equal to, omega comes out. So again, I'm writing sine cos. So minus b omega square sine omega. Now let us add these two terms. X equal to x double dot equal to this plus this. So derivative of this plus derivative of that. So that is minus a omega square cos omega t minus b omega square sine omega. That's the left hand side of this equation. So what is the right hand side of this equation? Right hand side of this equation is minus omega square x. Okay.
Time scroll down. See.
So minus omega square x. That is the RHS of this equation. So that is minus omega square into x. X is what? x1 plus x2. A cos omega t plus b sine omega. Now you multiply minus omega square a cos omega t minus omega square b sine omega. Now you look at the LHS and RHS. This is LHS, this is RHS. Correct? So LHS is equal to RHS. So hence, I proved that x double dot is equal to minus omega square x. Or in other words, what we have proved is, if x1 is a solution of this equation and x2 is also a solution of this equation, then x1 plus x2, some other x, is also a solution of this. So this is called the superposition. And this happens because this equation is linear. This is a linear differential equation. It's actually a linear second order differential equation, but the linear part, linear equation, the property of a linear equation is that if x1 is a solution and x2 is a solution, then the superposition of those two equations is also a solution of this equation. So we have seen one interesting property of the solution of the differential equation, which is nothing but the equation of motion. So just let me write it down here. Equation of motion of what? Of an oscillating mass. Okay, don't forget that. So this oscillating mass is a classical. So what is the word that, why am I using the word classical? Because you know that these are applicable only to larger particles. What do I mean by larger particles is, anything that starts from a dust particle to even a planet. Okay, all this, according to us, is small. Sorry, large. Small meaning anything smaller than, let us say, it is not a strict line, but anything smaller than nanometers or a few nanometers is what we call small. So when we come to that size, we do not know whether this is going to work. So that's the reason in larger sizes, we use Newtonian mechanics, which we call classical physics. What I have done is I have used the Newtonian mechanics, simply used Newton's second equation, F is equal to ma, and F is equal to minus kx. And we found this equation d square x by dt square minus omega square x. We have found that this equation has solutions in the form a cos omega t. And suppose there are two solutions, x1 and x2, then the sum of these solutions is also a solution. This property is called superposition. Now let us see what is the energy of this oscillator. What is the energy of this energy? So first let us write down the potential energy. Okay. The potential energy is defined as between 2 points. If you take 2 points, B and A, it is written as negative of the work done, A to B. So this is the work done, force into displacement, Fx dx. And in our case, this is going to be, if you start from a point 0, let us say you move to a point x naught, I will call it 0 to x naught. Okay. Or if you move from a point x naught to x, then you write x naught to x. X naught to x, and this would be v of x minus v of x naught into kx. This is coming from here, kx. Okay, this is kx, so this is coming from kx into dx. Okay. So now, if you have a point, let us say x naught, and there is some other point x here. Instead of the point x, if I shift the origin to x naught, okay, which means if I make the x naught as the origin, then x naught will be my new 0, and x will be this quantity, which is x minus x naught. This earlier distance was x. Now this distance is x minus x naught. Sorry, this is x naught. This is x minus x naught. So this would be x minus x naught. So I can write this as v of x minus x naught. This is v of 0. That would be 0 to x minus x naught kx dx. Minus is there. There's a minus outside and there is a minus here. So minus minus will become plus, and integration of kx will be kx square by 2, and the limits are 0 and x minus x. x naught. V naught, we consider the initial position. The potential is considered to be 0. So this will be 0. This will be V of x minus x naught. So what we are going to have finally is, if I just write this as kx minus x naught square by 2 V of x minus x naught. So this would be equal to, in general, kx square by 2. So this is the potential energy of the system. We call it 4. I think this is something that you must have done in your +2. I'm just repeating it. So basically what I did is I defined the difference in the potential energy is defined as the negative of the work done. I think you must have studied it like this. VB minus VA to the minus W. Because you have to do work against the system in order to push this spring. If you push the spring, what will happen is the energy will get stored in the spring when you push it this direction. So you are doing work against the system. So the force and the displacement will be opposite direction. That is why you have a minus here. That's all I have written. And that minus sign, the work done or the energy is nothing but force into displacement, which is integral of force into displacement, because the entire length you have to consider. Then I have got the potential as kx square by 2. Okay. So this is the potential energy. Sometimes I may say potential, but it is not potential. Okay, so this is a usual usage. Potential is not same as potential energy. But what I mean is potential energy. Now, what is the? Yeah.
Sir, if the system is vertical, then will the potential energy be same?
Then you will have to also consider the gravity.
Yes, sir.
I'm not doing that because that will add one more level of complication. So that is not necessary for our present discussion. To do that, you have to take the gravitational force also.
Yes, sir. Sir, then the original equation will also change, no?
Yes, it will change.
Okay, sir.
Yeah. So now let us write the kinetic energy. So the kinetic energies, I will write it as, okay, kinetic energy. It's half mv square. Half mv square will be half m. P is nothing but x dot square. Now let us write the total energy of the system. So the total energy of the system E equal to half mx dot square plus kx square by 2. So this is and this quantity is called the Hamiltonian. Half m dot square plus k square. So the total energy is written in terms of the momentum. Why momentum? Because if you look at k E is equal to half mv square, I can write this as half m v into v, right? But m into v is momentum. So I will multiply another m here. And to cancel that m, I will write an m here. So it will become half 2m p square. That p is equal to m into v. So you can also write this as h equal to half p square by 2m plus kx square by. So now we are going to look at a second property of the system. So if I draw only the potential energy, it will look like this. So this will look like a curve, which will look like this. So this is potential energy, V is equal to kx square by 2. Okay. But you can easily show that suppose you do this, E equal to half m x dot. Okay, suppose you take x equal to a cos omega t, x dot would be minus a omega sine omega t plus k into this. I'm writing this part. Okay. So half m x dot square. So square here. X would be k cos omega t square by 2. So half is outside. Half I'll get outside. I have minus a n omega sine omega t square plus a cos omega t square. Okay. Now if you take half, this would be minus a square, right? A is out, m is inside, outside, so m is not going to get square. M omega square sine square omega t plus a is not outside, so inside here, k is not going to get square. A square cos square omega t. 2 is also outside, so 2 is already there. Okay. So half. I can take a square out. Yeah. So omega square is what? K by m. So k by m. M is there. Sine square omega t plus cos square omega t.
Minus.
Pardon?
Negative sign.
What?
Negative sign, sir. Minus.
Where? This
Sir,
point.
that minus a square m.
Where is the minus a square m?
It is minus k, no, sir. Here. At last step, sir. Last step.
Okay, minus here. Here.
Yes, sir.
Yeah, but there is a square, no? So you're doing the square, so it will become plus. Square become plus here itself. Your minus 1 square will be plus. Correct. So take a minus
sir.
here, no? Minus a
Yes,
square.
sir. Yes.
Okay. So a square by 2. Now mm goes, right? You have k on both the sides, so k comes out. So this would be sine square omega t plus cos square omega t. So this will become a square k by 2. This is 1. Energy is, so the total energy is constant, doesn't have any dependence on time. The total energy is constant. So you see that the total energy is constant. That is one thing that you observe. And second thing is, of course, when the oscillation happens, it will change between the potential and the kinetic energy. But you see the potential energy is continuous, and therefore the kinetic energy is also continuous because it is continuously feeding into. So if you compress the spring, the energy will get stored in the potential form. If you release it, it will go in the kinetic form. Since momentum is continuous and position is continuous, the total energy will also be continuous. So that is the second property that we have seen, that the energy is continuous in a classical harmonic oscillator. Okay, so we have seen two things today. One is when you consider a harmonic oscillator, a classical harmonic oscillator, the solution obeys superposition principle. Solution of the harmonic oscillator obeys superposition principle. So this is the equation we found: square x by dt square minus omega square x. Solutions x1, x2, x3, if you take like this, suppose there are many solutions, sigma xi, I is equal to 1 to n. If you add all of them, x is also a solution. This is called superposition. The second thing is we found that energy of the harmonic oscillator, classical harmonic oscillator, is continuous because E is equal to P square by 2m plus V. Okay. Where V is kx square by 2. Because P and x, the momentum and the position are continuous. Okay, so these are the two inferences that we have drawn from this analysis of classical harmonic oscillator. Okay. So with this, I am going to stop here. So what we have done today is we have shown that we have considered a mass attached to two springs. Of course, there are certain assumptions that the springs are massless. Okay. Otherwise, you have to consider the mass of the spring also. And then we have shown that its solution is a sinusoidal solution, and the superposition of the solutions is also a solution, right? And finally, we have also shown that the energy of the harmonic oscillator is continuous in nature because the momentum and position are continuous in classical physics. So in the next class, we will take one example, which is that of the hydrogen atom, and we will see that there is a problem and we do not find it is easy to apply any classical laws of physics to describe that. And therefore, we realize that when it comes to subatomic particles, we have to invoke different kind of a law. And we will be looking at the necessity for formulating new laws which are different than classical laws, which will show the differences, and we can make a comparison of what the differences are compared to what we have done today. And you can see there will be many interesting features which would look much different than what we have done today. So for the sake of comparison, I've shown you the definition of the derivation of solutions of the simple harmonic oscillator. So we will stop today. And if there are any questions, I can answer them. So any questions, please let me know. You can also put them in the chat box. Otherwise, we can close.
You have to take the attendance.
Pardon? I think, Sirius, are you there?
Yes, sir.
So there must be some way of doing that in I guess, in the Zoom. Or you can just copy the names right now and then paste it somewhere. Take a screenshot or something. Okay. I will check later whether it is possible to take them. Or you want to make them put in the USN IDs? Okay, those who are those who are NMMIT students, and because there are some other students as well, they can write their USN ID in the chat box, please, so that someone can copy. Shravan is asking, how can we apply this? I didn't understand what you mean by how can we apply this. Please elaborate your question. I will stop the recording.